So the thing with negative numbers is that they tend to arise when we have a situation where we've had to go beyond zero or beyond our starting point. And this comes up, say, in like temperatures. So we're going to get into negatives today. And if you think about, for example, like temperature. And actually, way up here, let me do this. Top, I'm going to put 212. 100. Now, this isn't drawn on the scale, but let's say this is a Fahrenheit temperature scale. Now, Fahrenheit temperature scale we're very familiar with in the United States. Water freezes at 32. I think it's 212 is when water boils. 100 degrees, that's the temperature that was the, well, most of the summer's temperature this past summer here in Roswell, from what I've heard, was over 100 degrees. Again, water freezes at 32. And then you do have zero. So now water's definitely frozen. You can go farther. You can get -1. The coldest temperature I've ever seen is -1. Now, some of you, if you visited like the Midwest, say, or you've been on top of the mountains in the wintertime, you've probably seen temperatures colder than -1. But the idea is that, well, things are colder. I mean, this is pretty cold. This is more cold still. So what we use for negative, when we deal with negative numbers, is we're saying that we're going beyond zero. So negatives can have that kind of a meaning. It's just below zero, so -1 below zero. Another use for negative numbers comes up in finance. So let's say we have your bank account. So with your bank account, you open it up, you start with zero. Usually they make you put a deposit there anyway, something, so it's not just zero. But then you can go up to 50, 100, and so forth. But it's possible to have a negative balance. For example, you could get hit with an overdraft fee. And so technically you would have a negative balance. Now, they won't always necessarily say it's negative. They might say that you owe $5, but technically it's a negative balance. So this is money that's yours. This is no money, and this is money you owe. So we can think of negative numbers as meaning that. Depending on how you're using them, they can take on different meanings. So positive is money that's yours. This is when you have no money. And this is money that you owe. So another way of thinking about this, pardon me, I'm just going to grab a paper towel real quick. Another way of thinking about this, let's say we have a budget. Now, a lot of this, if you have, say, your bank account, Bank of America, if you log into your Bank of America account, it adds money into your account, subtracts money, and will give you a total when you have the debits taken out and then the money that's deposited in accounted for. So you don't usually have to do this, but you used to have to do this by hand because you couldn't access it by computer. So you have to put in, what money that you have included and what money that you're taking out of your account. And just as a pro tip on these, with those, when you look up online to see what your balance is, I've encountered the situation where the balance is not accurate up to 72 hours. Again, just a pro tip that might be relevant. So, well, I guess I better tell that story. So what I did is I checked my bank account. I was going to go grocery shopping, and this was in grad school. And I had just enough money to get groceries. I'm like, this is great. What inspired me to go grocery shopping that day was a log of cheese that they had on sale. A big log of cheese. I was very happy about this. So, because I do a lot of things with cheese. And so I'm going to go buy my log of cheese. So I log into my bank account. I've got enough money. I'm fine. Make the purchase. And then I get a notice that I've overdrafted. I spent more than was in my account. And I thought this was strange. I just checked my account. I was fine. And then I talked to the people, the bank on the phone, and they said, well, if you check online, it can be off. In fact, it can be inaccurate and not include all the transactions up to 72 hours. So that means for the past 3 days, anytime I use my credit card or my ATM rather, those would not actually be counted in my total. I was like, oh. But they were kind enough to redress the overdraft charge. It was awfully nice of them to do that. So I'm very thankful that they did that. But just FYI, if you check your balance online, it might not always be accurate. So what you do another way is track it on paper. So what we can do is we will say positive numbers, money that goes into the account. So let's say we get a paycheck. But then we buy that log of cheese. So that's going to cost, say, $10. So we owe somebody $10. So negative $10. And then let's say I sell something on Craigslist or eBay. But then the electric bill comes in. I owe the electric company, golly, let's say $70. So what we do is we combine these numbers. We have a plus 20, and we actually add them all together. We treat these as negative numbers. Now, we can think of them as subtraction if you want, but we can also think of them as adding a negative. So this could be 200 minus 10. So I'm going to get rid of this for now. 200 minus 10 plus 50 minus 70. So that's going to give us 190, 240, 170. So plus 170 in my account. So that's money I get to keep. It's not negative, so I don't owe anything. So we could do it this way. 200 subtract 10 plus 50 minus 70. Another way of doing it is we can think of it as 200. That's money we get. Plus, but then we have to include the money that we owe. We get another deposit, and then we have money that we owe. So the idea of using negative numbers, it's another way of just labeling amounts of money. This is money that we get. A negative is money that we pay to somebody else. And so this is a key thing in negative numbers we're going to run into. That subtraction, what this really is adding a negative. These ideas are the same. So every time you see a subtraction, you can think of it as adding a negative. Every time you're adding a negative, you can think of it as a subtraction. So we can think of 10 minus 5 is 10 plus negative 5. Or we can think of 10 plus negative 5 as 10 minus 5. Either way is correct. So any questions about that? All right. So we're going to talk about the number line. And with number lines, we're going to get into this idea called absolute values. So number lines and absolute values. Well, when we talked about negative just now, we have this idea of going beyond 0. So the number line is usually centered at 0. You'll see people graph parts of the number line. Say part that's centered at 10 with the numbers around 10, just below and just above. But we often like to have 0 as the center. Positive numbers are on the right. Negative numbers are on the left. So you have negative and positive. Now, another property with the number line is that larger numbers are always on the right of smaller numbers. Larger numbers on the right of smaller numbers. So that means as you go from left to right, you're always getting bigger. Now this can give you some interesting results, and sometimes some curious results. So that means 3 is bigger than 2. Now, the way we express that is we say 2 is less than 3. This is a less than sign. You can think of it, and you might have heard of this, say, in elementary school or junior high, or high school, actually. But it eats the bigger number. So you say 2 is less than 3. Now, another way we can write this is we could also say that 3 is greater than 2. And my teacher, you don't actually put teeth in there. Remember my teacher always put little teeth in there to remind us that it's eating the bigger number. Now, when I talk about left and right, I don't mean left and right here. Not here, I mean on the number line. 3 is to the right of 2 on the number line. So that means 3 is greater than 2. And that's what we're going to have. Or 2 is less than 3, or 3 is greater than 2. And again, we get this interpretation from the number line. Now, you can get some results that are kind of curious. So example, take -3 and 1. in this case, because 3 is to the left of 1, or 1 is to the right of -3, that means 1 is bigger. So -3 is less than 1, or we can say 1 is greater than -3. And the reason we're interested in eating the 1 is because 1 is to the right of -3. So we're talking about these inequalities, and let me write these a little more formally. So what we can say is 1 and -1. 1 is greater than -1. So let's make sure we get the text. Or we can say -1 is less than 1. So 1 is greater than -1. -1 is less than 1. But both of these sentences say is that 1 is bigger than -1. And that's because 1 is to the right of -1 on the number line. So again, I'm just going to maybe squeeze this in your notes, but this is smaller. Bigger. So that's how we compare numbers on the number line. Now, there's another way we can do this. We could say this. 2 is less than or equal to 3. Now, this seems a little unnecessary. I mean, why not just say this? Why put this line underneath? This will become more apparent when we start dealing with x. We don't really deal with this until I think later in this chapter or chapter 2. We'll start putting x in here, and then whether this is here or not, it's going to have a definite meaning, a very important one. But here we're just stating a fact. 2 is either less than 3 or it's equal to 3. You have 2 options. You have less or equal. And as long as one of these is true, then this whole thing is true. Well, as long as one of these things is true, then we can use this symbol. I should say that. So one of these is going to be true. So in this case, it's going to be less. That's the one that's true. Now let's change it up a bit. So 3 is greater or equal to 3. There's two possibilities we have to consider. Greater or equal. So one of these two needs to be true for us to use this symbol. Oh, it's a little hard to see. So greater or equal is true. So in this case, it's the equal that's true. That's the one that's going to be the case. I'm just checking on my. Okay, barely see that. I'll try to write higher from now on. But in this case, it's the equal that's true. So questions about that. With these, you get a choice. So I'll do some more examples with those. So this can be a little confusing. Well, this is true. 2 is less than 4. Well, this is also true. 5 is greater than 3. This is also true. 5 is greater or possibly equal to 5. Well, in this case, it's greater. This one wins. Oh, sorry, no, they're equal. This one wins. But 5 could also be greater or equal to 3. So the equal one here, the greater wins here. Now, this is also true. 2 is less than or equal to 2. What makes this true? It's this right here, the equal. So these are all true. 2 is less than 4. 5 is greater than 3. 5 is greater than or equal to 5. Well, this part of it's true, so we're good. 5 is greater than or equal to 3. Well, that part of it's true, so we're good. 2 is less than or equal to 2. Again, that part's going to be true. But then here's some false ones. Six is less than 2. No, it's not. That's false. 6 is less than or equal to 2. Well, this is false again. 6 is not less than 2, and 6 is not equal to 2. This one's no good. 5 is greater than 10. 5 isn't greater than 10. 5 maybe is greater than or equal to 10. Well, it's not greater than 10. It's not equal to 10. That's false again. So that's how we use these inequalities. Any questions about that? So now we talk about absolute value. Basically what an inequality says, it tells us which number is to the right on the number line. So if we say this, what this is saying is if we draw the number line, five will be to the right of negative 24. That's what this is saying. If we take the other one, if I'm going too fast, let me know. What this is saying one. So again, what this is saying is 1 is to the right of -2 on the number line. So there's 1, and there's -2. Right, left. So that's what these inequalities are telling us. Are you to the right, or are you going to be on the left? Now, what about distances? There's another thing that tells us about distances, and that's called absolute value. So what absolute value is, it's the distance from 0. So, for example, if we take a look at 3, it's 3 units from 0. There's 1, there's 2, here's -1, here's -2. But this one's also 3 units from 0. So what we say is this: the absolute value of 3 equals 3. And then the absolute value of -3 also equals 3. So the absolute value of 3 is 3. The absolute value of -3 is also 3. Now, questions about that? So what we've got in this situation, I get kind of tired of writing absolute value of, so I'm going to make a symbol. Instead of saying the absolute value of 3, I'm going to write this. That symbolizes absolute value of 3. Now, what is that equal to? Well, it's still equal to 3. And then the absolute value of -3, well, that's still 3. Nothing's changed. So this is absolute value, absolute value. So we're working on a symbolic language here in mathematics. And we do that sometimes just because it's faster. So basically, what does absolute value do? It makes negatives into positives. And then positives stay the same. So negatives become positives, positives stay positive. That's absolute value. Now they mention equivalent fractions in here. We've worked with these already. I'm going to go on to more negatives. And then we'll review the equivalent fractions. We will review them. So let me do some examples with absolute value. Now, one of the things with absolute value is we actually treat them like parentheses. That's just sort of a space there, illustrated with a dot. So absolute values are going to treat like parentheses. So what does this mean? So if we have calculations inside absolute values, we do those first according to PEMDAS, just like we would with parentheses. So let me give you an example. For a good example. Not quite what I'm looking for. Let's do this. So let's say we have something like this. What we're going to do is we'll do this calculation, these calculations first. We're going to treat the absolute values like parentheses. Now, if we think about what PEMDAS is, PEMDAS is going to be our order of operations where we do parentheses first. So if we're going to treat absolute values like parentheses, we got to do these calculations first. And we have to choose, do we subtract first or do we multiply first? Well, multiplication and division, if you remember, are grouped together. And then below them, addition and subtraction are grouped together. So that means multiplication is before subtraction. Now we subtract. Now, why is this -4? We haven't talked about that yet. We're going to hopefully get to talk a little bit about that today before we're done. But 2 minus 6, if you put that in your calculator for now, you're going to get -4. How to calculate this without a calculator, we'll do that in a little bit, hopefully have time. So now you have 25 minus 2, absolute value of -4, subtract 4. Well, the absolute value of -4, well, absolute value makes negatives positive. So that means this will become positive 4. We want to deal with our absolute value before we do anything else. So now the absolute value is gone. We just have a multiplication here. And this actually symbolizes multiplication. We're going to go over that actually after this. Why is 2 next to a parenthesis mean multiplication? It does. In algebra, it does. So we have to choose between subtraction, multiplication, or subtraction. Well, multiplication again is first, according to PEMDAS. So now we subtract as we go left to right. So 25 minus 8, 17. And then 17 minus 4 is 13. And that's going to be our answer. But the key takeaway from this, we do all the calculations inside the absolute value first, and then we resolve the absolute value. You know, if it's a negative number, it's going to become positive. If it's positive, it stays positive. Now I've got this here, and somehow I knew this meant multiplication. So I got to talk about symbols in algebra. Let me grab it with a pen. So for operators and symbols in algebra, we're familiar with many of these. We've seen these from arithmetic. So they're not all that new. Some things we, kind of are. We've seen the inequality signs. So we've seen like 5 is greater than 3 or 2 is less than 4. There's some other ones. Five equals 5. Or we could say 5 is not equal to 4. So when 2 are the same thing, they're equal. If they're not the same, they're not equal. Now, for addition, five plus 4. This is the symbol for addition. Or you could say the sum of 5 and 4. So addition or sum. Subtraction. There's different words for this. You can say 5 subtract 4, or 4 subtracted from 5. Say it 2 different ways. So subtract. We could say 5 minus 4. These are commas. Or we could say the difference of 5 and 4. So far, for these operations, whether addition or we use the word sum, they all need the plus sign. In fact, we can put plus in here. This is the symbol for subtracting, minus, or difference. All right, barely, we've seen some of this before. When we get to multiplication, it gets a little, you say, complex. So multiplying. This is going to be its own thing. Give it a little subtitle here. Multiply. So times the product. Sometimes, depending on how you use the word of, half of 10. We saw this earlier. That means 1/2 times 10. So multiply times product, or how we use of with fractions. So that's 5 times 4. So is this. There's 2 ways of writing it. Actually, there's another way of writing it. If you put 2 numbers in parentheses, that means 5 times 4. Or if you put a number here and a number like that, that also means 5 times 4. Or if you put this one in parentheses and that one not, that's also 5 times 4. Let me see if I'm missing any here. Also, if you take 2 variables, x, y, this equals x times y. This is x times y. Or, and we saw this a little bit, or we haven't actually, we'll see this later, but this is 3 times x. So when you have a number next to a variable, it's 3 times that variable. These two can be kind of confusing. But this is x times y. This is 3 times x. So you can represent multiplication all these different ways. So we'll run into these throughout. Finally, division. This is its own thing. Divide, quotient. Those are probably the 2 most common references. Let me see, do we have any others? That seem to be the common ones. Maybe ratio or fraction. Those are actually referring to division. Say fraction. So symbols for this. We know this one. The reason we use this symbol, it looks like you got a fraction bar with a top dot and a bottom dot. So here's a fraction bar, there's a top number and a bottom number. They all mean the same thing. You might see it written like this. And then, of course, we've seen this. They all mean to divide. So this is the symbolic language of mathematics. Any questions about that? So we have grouping symbols. Let me check one thing. I'm a little surprised that they're doing this. They're introducing grouping symbols after we've done PEMDAS. I figured that's a little confusing, but that is what they do. So grouping symbols. There's really 2 kinds. I mean, you could argue Well, first off, parentheses. There's numbers or calculations in between. Brackets. Numbers or calculations in between. Absolute value. They act like grouping symbols. There'll be numbers or calculations in between. Occasionally, they say this in the text, occasionally you'll see braces, what are called curly braces. These aren't really used much anymore. They have a special meaning in a kind of mathematics called set theory, and you usually don't see these because they get confused with what's called a set of things versus a group, like we're grouping calculations. But what that usually looks like, there's a hierarchy here, is typically what you'll get. Excuse me. Parentheses, and then brackets, and then curly braces. You'll see something like that. I've seen it where if they're not using curly braces, they'll use just more brackets. I've also seen people alternate with parentheses, brackets, parentheses, brackets. So that's another way you can do it. But typically, we're going to be dealing with just brackets and parentheses like that. So the last things to mention, we have equivalent fractions, and then we have opposites. We'll look at some algebraic expressions and formulas. So going back to negative numbers, opposites. They're numbers that differ by sign. And that's it. They only differ by sign. So -3 is the opposite of 3. Or 1/2 is the opposite of -1/2. So those are opposite numbers. They only differ by the sign. And a property of opposite numbers, if you take their absolute values, you get the same thing. So they have the same absolute value. So absolute value of -3 will be the absolute value of 3, which is just going to be 3. And the absolute value of 1/2 will equal the absolute value of -1/2, which is just 1/2. They have the same absolute values. They're the same distance from 0. Questions about that? So equivalent fractions. let me see, how do they describe them here? Because what you get them from is you get them from basically multiplying and dividing top and bottom by the same number. So again, this is sort of like fractions that are reduced versus when they're before they were reduced. So what they are, they look different. But they're the same quantity. So they look different, but they're the same quantity. So what that means is if we take, and we've seen this already, so this is a review, but it's not a bad review. If we look at this, and then let's take a look at the same sort of rectangle square. This is 2/4. That's 1/2. But these are the same quantities. It's the same amount. But you can express them as 2 out of 4 or 1 out of 2. And that means these are equivalent fractions. 2/4 is equivalent to 1/2. And again, this is the same thing as reducing fractions, same idea. So in general, to come up with equivalent fractions, we either multiply top and bottom by the same number or divide top and bottom by the same number. So we're going to generate these one of two ways. We can multiply top and bottom. By the same number. Or we divide top and bottom by the same number. So we can multiply top and bottom by the same number or divide top and bottom by the same number. The results will give us equivalent fractions. So let's take an example. Let's take 2/4. So let's start with method 1. So method 1 says we multiply. So we multiply top and bottom by the same number. So let's just pick a random number, say 3. So we multiply top and bottom by 3. Well, if we do that, we'll get 6 out of 12. So we find that 2/4 equals 6/12. Those are equivalent fractions. And you can see this. Half of 4 is 2, half of 12 is 6. They mean the same idea. Or we can divide. Let's divide top and bottom by 2. If we do that, we'll get 1 and 2. So that means 2/4 equals 1/2. So 1/2 is equivalent to 2/4. 6/12 is equivalent to 2/4. So those are equivalent fractions. Now what we're going to be doing in the next section when we start adding and subtracting fractions, we're going to need to be good at this. We want to be good at generating equivalent fractions. And for a particular reason, it's called finding a common denominator. So any questions about that? Now this is a packed section. There's a lot of little sub pieces in here. So we'll probably, looks like we're just going to get through section 1.1 and we'll be doing 1.2 probably later. So 1.1 is kind of a busy section. We start well, we've done common denominators. I'm sorry, you've seen that already. I just hit me. The next section is going to be adding and subtracting negative numbers. But we're still not done with 1.1. There's a lot in this section. So in this section, we finally get to work with variables. So this is the thing that can really unnerve some people in algebra. When you start mixing it with numbers with letters. Now, to be fair, what's going on here is we're looking for unknown numbers. I'll give you an example. 3 times what equals 12? It's a riddle. There's a number that's missing. What is that unknown number? And you would look at this and say, well, it's got to be 4. So the mystery number was 4. So this here is a variable. When we're missing a number, we call that symbol representing the unknown number a variable. A variable is a symbol representing an unknown number. So what does this tell us? Well, it's an unknown number. So that means it is a number. And we can do to a variable anything we do to other numbers. But because it's unknown, we might have to pause until we discover or until we're told what specific number we're supposed to use. Because variables are numbers, we can do to them all the things that we do to numbers. The only thing that stops us is we might not know exactly what number we're dealing with. So we might have to wait until, and I mentioned earlier, to discover or be told which number the variable is. There's a lot of writing in this part. We should be to the end of it. The trick with variables is that we might have to wait to discover or be told which number the variable represents before we can do our calculations. So if you have a variable in a calculation, you can't do that calculation until we know what number the variable represents. We can't do it. So for example, oh here, I'll give you another second to write that down. So we're going to look at some formulas, hopefully before class ends today. And we won't be able to do anything with those formulas until they tell us which numbers that the variables in those formulas represent are. So here, let me show you. So 3 times a variable plus 2. What is that equal to? I don't know. No idea. Totally clueless. The reason I don't know, you got to identify the variable. You got to tell me. It's sort of like Bob, someone, and Sally are showing up to the party. So give me the names of all the people showing up to the party. Well, I can tell you Bob. I can tell you Sally. But you didn't tell me who the second person was. You got to show me. This is a very small party. This is sort of a sitting around the table at Starbucks party. Get some nice lattes, get some whipped cream. Okay, and it has to be outdoors now because of COVID and everything. All right, moving on. We need to know what this is before we can do the computation. We do know, though, because it's a variable, it is a number. We just don't know which one. So someone has to come along and tell us. And we'll say, let the variable be 7. Thank goodness. Someone comes around and says, let this be 7. Now we can do the computation. We get 3 times 7 plus 2. Multiplication before addition, we'll get 21 plus 2, or 23. So we couldn't do the computation until someone told us what the variable was. Now sometimes we discover the variable. And you'll see it written like this. Solve for our variable. Now we've done this already. 3 times the variable is equal to 12. So we're answering a riddle in this case. You can sort of think of it as, well, you've fallen down the tunnel in the goblin caves, and you're there with Gollum, and he's asking you riddles. What was the one? Treasure chest without lid or lock, but inside gold is hid. What's a treasure chest that doesn't have a lid or a lock, but there's golden treasures hid on the inside? It's hidden in there. What could that be? It's a chest, no lid or lock, and there's a golden treasure on the inside. Well, if you've seen the movie or read the book, I think this is in the book, this line, the answer is an egg. An egg is a container with no lid or lock, and there's something golden that people like, egg yolk. So in a sense, it's kind of like a riddle. So we're going to solve for this. This 3 times some number, and that's the clue that we have, it's a number, gives us 12. And we saw this earlier. The variable is 4. So we discover the variable. So that's what a variable is. That's the idea. Now, for various reasons, and I don't know exactly why, I have a speculation as to why. Instead of using a box with a question mark to represent an unknown number, we use X. When we represent unknown numbers, we don't write this, we use that as the symbol. Now, why is that? Well, there's a number of reasons you can come up with. For one, when a lot of algebra is being developed, it's done in a time when there's not a lot of resources, at least not as many as today. There's no electricity. This is centuries, golly, that you're looking at over a period of maybe 2,000 years. There's no electric lights. You're doing this, if you're doing it at night, you're doing it by candle or fire. Paper or papyrus is, or bark, or clay tablets. Those are not as plentiful as, say, what we have today with dry erase boards and the paper that we use. So it's to your advantage, since you have to, lighting is more costly and paper is more costly, ink is more costly, and perhaps the whole process of writing on tablets and writing on papyrus is a little clumsy, using basically a reed with a dipped ink tip. It's easier to write stuff like this, just // that represents the unknown number. But why letter X? Why not use like L? That's a pretty easy one to do. Why not use that? Well, the problem is L could look like 1, A could look like 9. Depending on your handwriting, you could confuse certain letters with other numbers. O would look like 0. Z could look like 2. Again, T could look like 7. S could look like 5. X really doesn't look like any other number. So speculations as to why you could use X. It's a simple symbol. It doesn't require much. And if you're also writing this a lot, like you're solving for X, you're writing X a whole bunch of times, writing this gets kind of tedious. Complex symbol can get kind of tiring. So in the old days, probably took up some resources. It's tiring to write. And this doesn't look like a number. So we can use X as a symbol. So that's, and then if you use other symbols, you might, if you use, say, triangles, someone might draw a triangle for a variable. You might do it really fast. Looks like the number 4. Things like that. So for whatever reasons, there are some you can think of. We decided to use letters for variables instead of complicated symbols. And then we used X, I think mostly because it doesn't look like other numbers. So we're going to use X. So what we'll get, so if we compute this, we'll get 3. And remember, we write variables next to numbers to mean multiplication. So this is going to mean 3 times X. Again, that use of the symbol for multiplication. So then we'll say let X equals 7. We're doing that same computation we did before. So we get 3. And then what we typically do when we replace a variable with a number, we put it in parentheses. Again, that symbol for multiplication. So 3 times 7 plus 2, and we find it's 23. Questions about that? We're busting out our symbolism for multiplication. If you're kind of uncomfortable with this when you're just learning it, if you want to just write in that, or write in that, just to start, that's okay. But eventually you're going to see me as we get into class, we're going to be using the other notations. But until you're comfortable with it, if you're getting used to the idea of just variables, then do it this way. And once you're comfortable with variables, go back to the algebraic symbols for multiplication that we typically use. So we won't get the formulas today. I'm going to do one more, the discover one, and then we'll just have to stop. We'll get to formulas and algebraic expressions next week. But this is an important section. We cover a lot of stuff. This is the language of what we're going to be doing. So it's okay to spend some more time. So we're going to solve for X. So again, we have 3X equal to 12. This means 3 times X. So you can put your little times in there if that's going to help. So 3 times some unknown number gives us 12. That unknown number has to be 4. You can guess that. questions about that? All right. So what I'm going to do, we've actually done algebraic expressions, we just didn't realize them. That's it for today. We'll do lab in about 14 minutes. And if you have any questions, let me know. Otherwise, I'll see you in lab.